Okay, we might as well get going. Welcome to Monday, February 24th. Here's what we're going to do today. So I'm going to do a little Unix tip of the day, real quick one actually. So I posted the homework for assignment 3. Homework 3 is on the website. I put a little note on Piazza if you want to go find out some of the details. But it's on the website. It's due next Wednesday night. So a little over about a week and a half. And should be all right. I'll talk about that in a few minutes. Then we're going to talk, so last week we talked about binary trees and how sometimes they can end up in these weird degenerate cases. Well, this time we're going to talk about balancing trees, a particular type of tree called an AVL we're going to talk about. And then we're going to see if there's a way that we can actually represent trees in arrays, which seems a little odd when you first think about it, and you say, well, what does that actually mean when you represent it in an array? It's got like a left and a right pointer nodes and this, but we'll get into that, and you'll see that it's actually kind of clever the way we can do that. Okay. Any questions before I get going? All right. Okay, so I posted homework 3. So if you've looked at it, if you've looked at it already, you'll notice there's actually a lot of code in there. I've added another class called a calendar class. I've actually increased the size of the, added a few functions to the day class and the event class. And one thing that actually led to was me saying, all right, look, I understand. I know I told you guys that I was going to have you take a look at your or use your old code in assignment 3, but actually it's not as easy to shoehorn your old code in. I mean, it wouldn't be impossible, but it would be a lot of copying and pasting from one file to the other, and I didn't think that was really necessary. So so for those of you who are worried that your homework 2 code didn't work, you can rest assured that that is not going to be part of homework assignment 3, for what it's worth. There's a lot of code in there. You actually don't have to write that much. I mean, I think it's a total of maybe 6 or 7 functions. I mean, that's about it. There's a couple that I think are a little tricky and will take a little time to kind of figure out before you start writing them. And then there's a couple that are just kind of easy, like update the print method to actually print out the date as well. Because this assignment we actually have dates as well as the actual event times. And I spent like half the weekend writing all this code, and I can tell you one thing. Times and dates are kind of screwy when you actually have to convert between dates and times, and it's kind of painful. So I think I did most of the groundwork for all that, so you don't have to worry too much about that. But there's just lots of little things you have to think about when you talk about time zones, and when you talk about leap years, and when you talk about leap days, and all that kind of stuff that I had to sit down and figure out, and I didn't want you guys to have to actually worry about that part of it. You can actually test this assignment if you want with your own Google Calendar data. So one of the things I built into it was kind of an import function that if you export your Google Calendar data into a little text file, it comes out in this format that unfortunately isn't comma separated, although you can import comma separated data into Google. They won't give you their data in comma separated form. So I had to write a little translator for that. Anyway, you can import it in and test it out. I've also given you some test data as well, kind of like last time. But again, our tests in the actual assignment are not all the tests you need to be running for the assignment. Okay? I need to make that clear so that you guys don't all of a sudden get to provide when we get that up and things break and you go, I never even knew. So just know that you do have to write some of your own tests. Okay? Due March 5th. I think that's about all I have for it. Any questions on homework 3? As always, if you think you're not going to be able to get it done, email me and we'll figure something out. We have lots of office hours this week and next week. On Sunday there's office hours. And you can feel free to ask questions about that. Okay? Please don't start next Monday. Just don't think that's a particularly good strategy. Anything else on that? No questions. Awesome. All right. So where did we leave off? The other day? By the way, I'm trying this new Microsoft Surface thing. I'm kind of a Mac guy, but I'm trying this new Microsoft Surface thing. The reason I like it is because it's got this cool pen that I can actually draw on the screen with. Let's see. How do I do this? Pointer options and then like that, so I can draw all over the screen. So that's kind of cool. And then it's got a little eraser thing too, so I can actually erase. anyway, I'm giving it a shot. So if I can't figure the details out here, we'll get going. Oh, I know what I forgot. I forgot to do the Unix tip of the day. Sorry. And I have to use putty to do this because I'm not on a different machine. Sorry, the font is hard to read. Well, I'll try to work on that. Here's the one thing I wanted to show you on Unix tip of the day is the function or the program called tree, actually. And it's actually kind of a neat program. It does what we had kind of built in class last week as far as printing out your directory structure as a tree. Yes. I know. I don't think there's anything I can do with it about it right now. I think that. Hang on, for putty settings? All right, let's see if I can do this. Change settings, appearance. Let's see. Adjust the mouse pointer. Sorry? Sorry, I'm not seeing it. There it is, colors with a URS, I see. OK, hold on. Default background, maybe? Well, we'll see, but is that going to change the font? Or the, hang on. Oops. OK, hold on. Apply. How's that? Hey, that's much better. All right, thank you. So anyway, so this is what the tree function does. It's actually pretty clever. If you go into a folder and then you just type tree, it actually lists out. This is actually a little too fast. Hang on. And not the best color either, but tree. And then pipe it through less. And you actually get a little tree of all of your files in this kind of cool format. So it shows you the nice little format. That's all I really want to show you that. It's not on all Unix variants, this program, but it happens to be on the ones we have. I don't think it's on the Mac. You can actually install it, but it doesn't come automatically. So anyway, if you want to see all your folders in a nice tree format without writing a program to do so, you can use tree. OK. All right, back to actual trees, the data structure. So last week, we left off on removing items from a binary search tree. And we said it was a little bit tricky. And it's not particularly hard, but we had to sit there and think about it a little bit. And you guys came up with some good suggestions. And in the end, I said, well, one good strategy is just replace, not the only strategy, I should say. One good strategy is replace with the smallest data in the right subtree. Replace the node that's actually you want to remove. So if I want to remove 2, right? If I want to remove 2, I'm going to replace it with the smallest data in the right subtree. That's the right subtree of 2. Smallest data happens to be 3. So 3 will replace 2. Okay? And then I have to recursively delete 3. But it's actually pretty easy to delete a subtree when there is no left child. And it happens that if you pick the greatest or the smallest data in the right subtree, you will always pick an item that has no left tree of its own. So then all you have to do is bypass it. So it's going to end up being 5 bypasses to 4 in the, actually on the, I should do it in the left because it is, oops, there's a problem with it. The 5 would end up, the left subtree would go to the 4, right? And then that one's gone, and then this becomes 3, like that. So you end up with, that's how you can do the removing. OK? So fair enough. Now, in many cases, what we kind of don't even bother doing is actually doing the removing. All right? So because it takes a few steps and it's not the most efficient thing in the world, OK, what we could do instead is just say, hey, let's do this thing called lazy removal, which means we just mark it as being removed. That means that if you ever search for it later or do something else with it later, and you get to that node, you check and see if it's been removed already, and then you ignore it as if it wasn't there. You can still go on. You can still use its pointers to go to the next nodes and so forth. But we just do that so that we don't have to actually do the removal. What are the benefits of that? Well, one of the benefits is that if there's duplicates, well, then you can just keep duplicates. And if the duplicates end number goes down to 0, it means it's not in the tree anymore. OK, that's easy enough. And if you're already keeping a duplicate list, then it's a no-brainer to just change your code to update to make it 0 if it happens and skip it. And then if you happen to be dealing with a type of tree data where you will reinsert a node, well, you've already got that piece there. So if you're going to like delete 2 and then replace 2 later, well, instead of moving everything around, just say 2 doesn't exist, and later when you happen to replace it, go, oh, it's already here, and I'm just going to replace it. So this is all just kind of a little extra code to make to make things more efficient in the long run. Okay? You might have a question about, well, look, if I'm adding all this extra code to do all these special checks, is that hurting my overall efficiency? Sure it is. But here's the thing, and we're going to start getting into this stuff in the next couple days. I keep pushing off a little bit because I want to get enough data structures under your belt before so we can really talk about it. But if you have to add a little bit of code to each one of those nodes, right? Or to handle each one of those node cases, that's not as big a deal as the fact that you may be dealing with millions and millions of nodes. So there's a scale here. You might do one little thing to each one, but in the end, the fact that you've saved some time compared to touching all the different nodes that we actually have, you actually end up saving some time. So there's trade-offs to be made, but in terms of what part you need to focus on, for things like trees and other data structures we talked about, focus on the number of elements in the actual tree. Like, that's the important part. If you have to do something else per element, well, that adds a little bit of time. But the fact that it's all about the total number of elements that we have to deal with. Okay, we will get into that a little bit later when we talk about some analysis of this stuff. Okay, questions on that about removing from a binary search tree? Okay. All right, so we sometimes saw that trees, even binary search trees, can become rather deep just because of the way you insert into them. Okay, remember, if we were going to insert 1, 2, 3, 4 into a binary search tree, right? We'd have 1, and then 2 would be bigger than 1, and 3 would be bigger than 2, and 4 would be bigger than 3, and you end up with this not very good tree structure as far as minimizing the depth, right? I mean, it's just a linked list in that case. Okay, there are no left nodes. And if you'd insert it in some other different order, yeah, you'd have a different tree, and it might be a better, in fact, it would have to be guaranteed to be a better, or the other direction, I suppose, tree. But what we want to do is we want to find a type of method to actually keep the tree relatively balanced, because the depth of your tree is what really counts in a lot of these operations that we're doing with trees. Okay, especially searching when we talk about binary search trees. Okay, so one idea would be, look, require that the left and right subtrees have the same height. Okay, so if we were to do 1, 2, 3, 4 in here, and we were to require that the left tree and the right tree had the same height, we would have to, when we inserted 3, we would have to say, all right, well, this tree has less, so we've got to move some things around to do this. So maybe we'll rearrange it and say 2 is this way, and then 1 is here, and then 3 is here, and you can come up with some ideas to do that, right? Not necessarily a terrible idea, except for the fact that if you do it just for the root, you can end up with things like this, right? Sure, it's balanced, right? The left tree is exactly the same size as the right tree, but guess what? It's still kind of a terrible tree. There's no branching in amongst the actual elements. So if you do it just at the root and say, hey, the left tree and the right tree have to be the same size, you can end up with not so good trees like that. Okay. Other ideas, okay, you could also say, let's insist that every node has a left and right subtree that's the same height. Okay, you could say, look, it has to be the same height. Well, first of all, if you have some non-power of 2 number of elements, right? You're not going to actually be able to, or I guess power of 2 minus 1 elements. You're not going to be able to get the right number to fulfill this requirement ever. But even if you were, okay, you'd have to, if you said, okay, there's going to be special cases where the last one doesn't work, and we'll talk about that tree in a few minutes, it still is kind of too onerous to actually make this kind of a decision every single time you insert into the tree. It's just too painful, and you'll spend way too much time inserting and rearranging the tree if you were to try to keep that guarantee. It would definitely guarantee a small depth, mean, that would be terrific. It would be the minimum depth that you'd actually be able to ever have in a binary tree. But in the case of making it happen, it's hard. Like that's the tricky part. Okay. So what do? Well, we actually have this other type of tree, okay, an AVL tree called an Adelson, Velsky, and Landis tree. Okay, 2 guys or 3? I don't even know. I think it's 2. But anyway, they designed this. And what they said was, let's compromise. Okay, let's compromise. And what we're going to say is that for every node, the height of the left and right subtrees for that node can only differ by 1, the height of those trees. Okay? So for instance, if you look at this tree right here, right? If you look at this tree right here, 5, its left subtree has a height of 1, 2, 3. Okay? And its right subtree has a height of 1, 2. That actually meets the requirement. Okay? This one, well, let's see. Let's look at 7. 1, 2, 3, and only 1 for the 7 to 8. Okay, so this is not an AVL tree. Okay, the one on the right here. Why? Because one subtree does. Now, individually, like the 4, that subtree is okay, 1 and 1. Okay, the leaves are all okay because it's 0 and 0. The 2 is okay, 1, 2, and 1. So we've got 1, 2, and 1 here. That one's okay. All right, but it's the root in this case that has the problem. Okay, so everybody get the idea of for each subtree, you can only have 1 maximum level difference. You can have 0 or you can have 1, but you can't have 2. So far, so good. We'll let that process for a minute. These things aren't. A lot of these things take a little bit of time to like wrap your head around. That one doesn't take too long, but some of these take a little bit of time to wrap your head around. All right, so what we have to do then is we have to keep the height information for each subtree, right? Well, for each node, rather. You have to keep the height information for each node. And as it turns out, the height of this kind of AVL tree is almost the logarithm of the number of nodes, which is actually what we want. Like on average, if you go through and you do all these, operations on it, on average, you're going to end up with a pretty good-looking tree out of it. Okay, it may have one section might have, each little individual subtree can have one difference in levels, but that's actually okay. And overall, the height actually ends up being pretty balanced. Okay. The thing is, though, you do have to, every time you insert into it, make those changes, like to make the tree meet that requirement. Okay. And how do you do it? Well, you kind of do it recursively is the easiest way to do it, not necessarily the most efficient, as kind of always the case. But recursively, you do it. You kind of start at the bottom and you check each node's subtrees, right, and check for the heights, and then figure out how to modify it so that it meets this requirement. And these guys already did that for us, so it's not like we have to reinvent this, right? And it's a pretty straightforward approach, although it takes a little while to get your head wrapped around it, like I said before. So let's say we wanted to insert 6 into this tree, right? So if we were to insert 6 into this tree, 6 is greater than 5, and it's less than 8, and it's less than 7, and now it would go right in here like that. Okay? Now, what would this upset? Would it upset 7? No. 7 has the left tree is 1, the right tree is 0. 8, the left tree is 1, 2, and the right subtree is 0. So that's not good. So it's 8's got the problem. Does it upset anything else? 5. Let's see. 1, 2, 3, and 1, 2, 3. No. Okay, so we would just have to figure out how to deal with this and change the tree around so that 8 meets the requirement that its left subtree is only one or less in height than its right subtree. Check? Got that? Yes, Tom.
But wait, I don't think it was balanced before, because before we had 6, 4 in the left subtree.
Let's see, hold on. So for 5, let's look. 5's height is what? 1, 2, 3, and 1, 2.
Oh, okay. So
right?
It's not the number.
It's not the number of nodes, it's the height, right? It's which is all the way down to as far as you can go down on one side. Yeah. Okay, other questions? Okay, all right. So let's see how we would do this, all right? So after the, let's see. We can fix this problem, like if we were to try to insert 6, using this strategy called rotation. Okay, and it's kind of clever. It's actually very clever, and it's kind of cool to do when you see it. And we'll go through this for the rotations. After the insertions, only the nodes on the path from the insertion might have their balance tree altered, right? So if you alter something over on this side of the tree, only things this side of the tree could be affected by it, right? On the right-hand side of the tree could be affected by it, because you didn't actually change anything on the left-hand side. I mean, you might go all the way up to the root, and the root itself may have different balance, but you only get one side that you'll have to actually deal with. Okay, so you only have to walk up the tree; you don't have to walk down the other side. Okay, we'll rebalance as we follow the path up to the root. And what's cool about this is if you are inserting an element into the tree, you have already gotten down to the bottom part of that subsection of the tree. It's not like you have to re-climb down there. Okay, and if you've done it recursively, well, the operating system and the compiler actually takes care of all the stack stuff of holding your position right. So it's actually pretty clever that once you're there inserting 6 down here, right? Once you actually insert 6 down here, you can say, okay, well, walk back up recursively, and you'll get up to the top. Kind of cool. Okay, so it works out nicely. All right, so let's see how this actually works. Okay, because the tree has any node has only 2 children, and a height imbalance. Okay, I've got some mathy things in here, right? If we call the node to be balanced alpha, okay, each node only has at most 2 children. A height imbalance requires that the 2 subtrees of that node differ by 2. There can be 4 different cases. Okay, and this is where it gets a little bit tricky. When you actually go to code this, there's like a bunch of cases, and you have to deal with each case. The nice thing is they happen to be symmetrical, which is kind of cool. So let's take a look at this. An insertion into the left subtree, okay, of the left child. Okay, so if we were to look at let's say 2, for instance, here, the left subtree of the left child. This is the left subtree. The left child is here, and the left subtree would be, we'll put it over on that side there. Okay, that would be the left subtree of the left child. Okay. Conversely, we've got the right subtree of the left child. So 2 is the one we're looking at, right? 2 is the one we're looking at, and left child's right subtree means we put it somewhere over there. Okay. Same thing goes for the other side. Okay, I mean the left subtree of the right child and the right subtree of the left child. The left subtree of the right child for 2 could be either here or here, right? And the right subchild of the right subtree could be here, or the right subtree of the right child could be only here for 2. Okay, there's 4 different cases. Everybody got that? Let's see how we deal with them. Okay, for the outside cases, the cases where we have either a left subtree of a left child, right? Or what we can do, or we have a right subtree of a right child. What we can do is we call this a single rotation, and we'll go through that in grave detail here in a few minutes. Okay, if we have that other situation where we've got a left-right insertion, things get a little hokey, and you have to do what's called a double rotation. It has to be a little more complex, but once we go through it, you'll see what it actually turns out to be. Okay. So here's an example. Okay, now I've drawn this kind of in a little bit of a strange way, but x, y, and z are like the subtrees, right? You can kind of see k1 and k2 are like nodes, and then they've each got their own subtrees, which may branch out and become bigger or smaller. Okay. So see how k2 is violating the AVL property? By the way, the little dotted lines in the middle, that's kind of like the level. So wherever the bottom is, that's what level it's at. So x happens to be at level 4, y happens to be at 3, z happens to be at 1, or sorry, 2, right? And k1 is on the same level as z. Okay? Can you see that the height of k2 is on the left-hand side is 1, 2 is from here, 1, 2, sorry, 3. And the height of the right side tree is only 1. That's violating the property, 3 and 1. Everybody get that? I know this takes a little while. I'm not going to try to fly through this. Yes?
This side is 1. K2 to Z is 1.
K2 to Z is 1.
Then why
1.
K2 to K1 should be 1? K1
It is.
to
1,
should be 1.
2, and then to the bottom of this whole node. This is actually, what this is representing is this whole subtree that's underneath K1. You see how it's a totally different, like it's why I made it a triangle versus a circle, right? Because it's saying that K1 is its own one, like one node. X down here is a whole complete subtree that happens to go all the way down to this level. Make sense? It's not just nodes. Yeah.
So Z should be a leaf.
Z should be what?
A leaf.
Well, it doesn't really matter. I mean, we're just saying that the leaves in this case are these other subtrees. Because it's all that really matters is the leaves are subtrees in this case. Okay, yeah, sure. Z happens to only have 1, so it could be a node, but you can think of a one node item as a subtree. It's a subtree of one item or one node, right? Okay. All right, yeah, sorry if this looks a little confusing, you got to go back and look at it, but wait till you see what we actually do. Okay. All right, so here's a visualization for you. Okay. We're trying to make it so that this thing is balanced. Okay, here's how you actually do it. Okay, for the side of the tree that's unbalanced. So if you look at K2 has its left-hand tree is unbalanced, right? If you grab the first node underneath that on that side, and you grab it and you shake it, and let gravity do its thing, okay? Pretend that this was like, actual weights or something, right? And you could do it, right? You would have K1 as the root, and we have to kind of figure out where everything else fits in. But it's not too hard, as it turns out. Okay? Take a look. We know what? We know that Z, whatever Z represents here, is greater than K2 in this binary search tree, right? So far, so good? This one's got to be greater. This one's got to be less. If K1 was all of a sudden at the top, we know K2 has to be greater still, so it's got to be, if K2 is somehow coming under K1 now, well, it's got to be in the right-hand path, K2. And this one does as well, of course. Okay? And we're not going to actually touch this other one, but we're going to end up making K2 go underneath to the right side of K1. Okay? Y is also less than K2. It's greater than K1 and less than K2. If we know that K2 is going to come off of this one here, well then Y has to be a left of K2. Okay, I'll show you that in a second. I'm just kind of describing what it is so that you kind of get the feeling. Here's what it ends up looking like. Okay, you have K1 and K2. K1 is now the root. We've grabbed it, we've kind of shaken it, and what happens is it actually raises up X, right, to the same level as Y, and it actually lowers Z because K2 has to go down 1 and be a child of K1. Okay, and do you see why it's kind of a rotation? You're like rotating the tree around like that. Okay, it's a little bit of a strange rotation. I mean, it's not quite as simple as just like, but it's rotating the tree around. Make sense? I know this is a little tricky. I see some people going, no, I don't get it. But I'll show you this, and we'll see an animation on it in a little bit. Okay? Questions on that? Makes sense, though, that now it is now still a proper binary search tree, and now it's actually balanced because K1 has how many different levels? 1, 2, all the way down to the bottom here, and 1, 2, all the way to the bottom here, and likewise over here. So far, so good? Okay. All right. Let's see how we might do this for that 6 that we tried before. Okay, if we try to put 6 in, okay, we end up putting 6 down here, and we go, hey, we need to insert it here because it's got to be less than 7. All right, it's going to be greater than 5, less than 8, less than 7. It's going to go right there. Well, if we look at the heights going up, 7 is actually OK because its left node is 1, its right node is 0. That fits the requirements. And then you go to 8. 1, 2, and 0, and 8's the problem. Okay? Well, so what do? You grab 7, and you shake it, and you pull it up to the top, right? And it falls out. And 7's going to come under 5 now. Well, 6 has to be less than 7, and 8 has to be greater than 7, so they fit in the tree like that and that. Make sense? Hopefully I see a few nods here. Okay, that's how we're going to actually do this rotation. Okay? All right. Turns out that going the other direction, if you have a right-right subtree, it's the exact same thing except the other direction. Yeah, question? Yeah. Yeah, single rotation is left, left, or right, right. Let's see. It is for 8. OK, so yeah, very good question. Very good question. Thanks. That's actually the reason that's a good question is because whoops. There we go. OK. For 5, it is the right left. But just if you go up one level, what is it for 8? So remember, we're going all the way down. Right? What you do is you go all the way down to the where it is, and then you start walking the tree back up until you find something that was problematic. Okay? You find a node that doesn't meet those requirements below it. Okay? So take a look at 6. Take a look at this one here. So 6 goes here. You are correct. 5 would have been a right left, but as we go up, 6 is not a problem. 7 is not a problem. 8 has a problem, and was it a left left or a left right? For inserting, if we were to forget about the rest of this, just look at 8 itself, pretend it's its own tree. You see how we inserted left, left? Okay, that's the issue there. Okay, we don't need to. Whoops. I don't know why I can't erase now. There we go. Ah. Can't do it. I don't know. Anyway, but you get the point. Left, left versus it's not from the top one. It's from whatever one gets upset by the balance. Okay? And the question is, does any other one get upset by the balance? We'll get to that. Okay? All right. But you get the idea on that one. Okay. Like I said, it turns out if you do the right, it's the same sort of thing. You grab the node underneath the one that's got the problem. You shake it, and that one ends up at the top. And you have to kind of figure out where the other pieces go. It's not that bad. You can actually do it recursively. And the recursive solution is actually fairly straightforward. Okay? All right. So let's take a look at this in practice. Okay? There is a visualization site that I'd actually heard about and then forgotten about. And then on Piazza the other day, Brett, is Brett here in this class or in the afternoon class? No? Might be watching on video. I don't know. Brett G pointed out that this website exists, and it's actually pretty cool. Like it's like the one I showed you last week, except like advanced. It's got like all sorts of stuff. It's got the linked list. It's got arrays. It's got trees. And it happens to have an AVL tree in here, okay, as well. And what I forgot to do is write down here. I'll write it down right here. Here's what we're going to do into these things. We're going to insert 3. That's terrible. Hang on. We're going to insert 3, 2, 1, 4, 5, 6, and 7 into an AVL tree, and we're going to see what happens when you do that. Okay? So I think I have it up here, as long as the internet's working. There it is. Aha! All right, I'm going to bring this down because you need more board space. Oh, 3. Hold on. 3, 2, 1. I have to peek under the board if I don't do this. All right. Here we go. 3, 2, 1, 4, 5, 6, 7. You'd think I'd be able to remember that. OK. All right. So here's what we're going to do. We're going to actually insert these into a tree, and the animation is going to show us what's going on. OK? All right. So what you do is you go over here and you say insert 3. And what it does is it creates a little thing. Now, this is really tough to see. I will grant you that. And in fact, it's not so good on the board here. I don't know why I did it over so far. But what I think I can do is this. Oh, I don't want to do that. Well, we'll see what happens. It's going to create a tree that we might not be able to see part of. OK, so anyway, you can see here that it's got a 3 in there. That is the actual the number that we are inserting. This little number up here, okay, is the height of this node. Okay, it's the only node in there that's got a height of 1. Okay, normally we would actually say it's got a height of 0, but for now, just pretend it's a height of 1, and this is how this program actually deals with it. Okay, a height of 1. All right, so now we're going to insert 2 into this. Now, this is a binary tree, right? So we know that it's got to go on the left. All right, so what it's going to do, it's going to take it and it's going to say, all right, it's going to go under there, and it's going to start walking up the tree, fixing the heights of each individual node. So now the 2 has a height of 1, and now 3 has a height of 2. So far, so good? I don't think that's too tricky. OK, now we're going to insert 1. Okay, and 1 is going to do the same thing. Now watch what happens here. 1 comes down, and it goes to here. Okay, and we get up to here, and 2 is for that, and 3 is there, and guess what? We've got a problem. Okay, so we do this rotation. Now, let me go back. Somehow back wasn't working perfectly well before, but I'll try it again here. We're going to insert 1, okay, and I'll pause it when we get there, just to kind of see what's going on. Okay, so 1 comes down, it's there, it starts walking up the tree, right? It gets up to here. Okay, and now we've got this situation where if you look at 3 here, its left child has a height of 2. Its right child is null, so it has a height of 0. We're out of bounds for this AVL tree. Make sense? So what do we have to do? We have to take the node that's got the problem, which is 3, has a problem with its left and its right nodes. You grab the one under it, you shake it, and what comes out? Well, 1 is going to end up to the left, and 3 is going to end up to the right of 2. That's all there is to it. That's what the actual rotation does. Not so bad. Yes?
Why does it need to go back up to 3 before it makes 2 the new root?
So it needs to find the root, or find the node that for whose left and right trees are screwed up.
But didn't it already see
Okay.
that
Well, okay. So did it already see it on the way down? It doesn't keep track of other things above it. Like if you're in a recursive function, remember you're not really keeping track of what's above you. Its job is to keep its track, right? So it's right now it's 2's job to keep track that it's a height of 2. It's 1's job to keep track that it's a height of 1. It's 3's job to keep track that it's a height of 1. And it knows, and it can figure out. You can return from your child what their respective heights are. So that's all it is. Okay. Good. All right. So let's see. That was 1. So now we're going to insert 4. See what happens. Okay. So we insert 4. 4's got to go here, right? Because it's going to be and everybody seems, let's see. So 2 and 3, is everybody OK? 1, 0, 0, we're OK. 2, 1 and 0, we're OK. 3 has a 2 subtree and a 1 subtree where it's OK. And then 1, of course, over here is OK. So we're OK. No changing necessary. Okay. Let's put in 5. Okay. It gets a little bit crazier here when you get more. Okay, 5 is going to also come all the way to, the pointer's dead. 5 is going to go all the way down to the bottom. And then as it walks its way up, let's see, hold on. Oh, there we go. I grabbed it in time. Okay, that's weird. Now like vibrating. So in this case, so look, 3 now has a problem. It's got 0 in its left tree and 1, 2 here. What do? You grab this one, which is the one that's pulsating, right? You grab it, you shake it down, and then 3 is now going to come to the left of here, and 5 is going to be there. Okay. All right, boom. And then it goes back up. And notice it only had to make that one change. It hasn't so far ever had to make a change higher up in the tree. That might be a good thing. Okay, it may never have to. Okay, because it's doing the bottom there. Okay, that was 5. So let's put in 6. All right. 6, same thing. All right, it's going to walk all the way down. Okay, and then 6 is there. It's going to walk back up. 2 and 1's OK. 3 and 1 is OK. And then 4 and OK. So here's a problem. I missed it. Hang on. Skip back doesn't work so well. Hang on. Let me try it again. I'll just pause it on there because you can kind of see. All right. Play. Oh no, I hope it works. OK. So it's going 5 and 6. And don't forget to hit pause. There we go. As it goes up, boom, boom, and back here, there. So now we got to have another little problem. This one didn't have a problem. It's 2 and it's 1, 2 and 1. This one had a problem because it went, all right, it's 3 on this side and 1 on this side. So now the root actually has the problem. Okay, so we need to do what? We need to rotate the one on the side that we inserted into. We grab 3, we shake it. So now, I'm sorry, we grab 4, we shake it, and it's going to be the top one, right? And so we know that what has to happen is the 3 has to be on the left-hand side here, but it's going to be on the right side of 2. The 2 has to be on the left of 4, et cetera, et cetera. Okay, watch how it does it. Okay. Shoop, like that, rotated right around. Okay, kind of cool. All right, and then finally, let's insert 7. Let's see what 7's going to do. It's going to come down here. It's going to come down here and go right here, try to go here, and then we might end up with some other issues. Okay, let's see. Insert 7, and it goes down, comes down, comes down. All right, and the first time we have a problem is right here at node 5. Right, shake 2, let's do it up, and then all of a sudden 3 doesn't have a problem anymore. So you never have to do it more than once, which is kind of cool. Okay, you're only going to have to do once, and by the way, at the end here, you end up with a perfectly balanced, perfect tree. Yes?
I don't understand how the pointers move around.
Ah,
Because when the
don't understand how the pointers move around.
ball gets the 5,
Uh-huh.
it changes the pointer for 4 to point to 6.
Yes.
How does
Yeah.
that happen?
You do have to keep track of the pointers as well. So in your solution, you have to keep track of the pointers. The nice thing is you always know who your children are,
Yes.
so you can go child to child if you need to.
But you don't
Right.
know who your parent is. And
Ah, you do. Well, yeah. Okay. Again, and this is a really key point. You don't know who your parents are, right? You don't have links back up. Fine, fair enough. In a recursive solution, if you're doing this recursively, the fact that you're calling something from a recursive like function means that all that stuff gets stored for you, right? So when this one returns up to here, this one is done acting, it returns. Well, it got called by this one, so therefore you're back at this one. Okay, it's the whole point of a recursive solution, which is kind of cool. It looks kind of crazy because it seems like you're going down and then you're somehow turning around and walking back up. It's not turning around and walking back up. It's returning from the function. That's the part that, yeah, and we talk about recursion all the time, and that's the hard part about it. Getting your head wrapped around what does that mean? Oh, I'm in the function. I'm calling something. It's returning. Hell, I'm back again. That's what's going on. Okay. When we get to the end, at the end I'll show you a little recursive thing. Maybe I'll bring this up again, and then I'll kind of walk through that, and you'll see. Okay. I know it's tricky. Other questions on this? You can go to this website and you can play around all you want. Yes.
Do you have to call from the root?
Yeah. So what you do is it's just like anything. Where do we start inserting? If I'm going to insert 8 into this tree, I start from here, and I say, is 8 bigger than the root? Yes, it is. Go this way. Is it bigger than this? Yes, go this way. Is it bigger than this? Yes, go this way. You see, so you always start at the root. And that means the top call that you have is from the root. Okay? Now, you might say, okay, look, Chris, you say all the time recursion is not really a great solution. You got all these stacks and things, and the stack is not an infinite size. So can't this like recursive? Wouldn't you want to write it in a non-recursive way? Think about it this way. The whole point of doing this is to keep the tree balanced. What did we say the number of the total height of the tree is on the order of? Log n, which means that you're never going to have to recurse more than, well, on average, more than log n or maybe log n plus 1 times down the tree, which is great. Okay, you don't have to go that deep. So a recursive solution, while slightly slower, is actually not a bad solution here because you never have to go so deep. Okay, that's what it's all about. All right, any other questions on this one? Okay, let's get back to this. Okay, all right. So what happens if we do have that right-left or left-right insertion? Okay, so take a look at this. So we started with a nice balanced tree or an AVL tree, and all of a sudden we inserted something else in this tree and made this level, either this side or this side, we're not sure actually, but we made this level too deep. Okay? If we tried to do that rotation that we did before, right? Because K2 has 1 on this side and 1, 2, 3 levels on this side. If we tried to do the same thing with K2 where we grabbed K1 and shook it, look what happens. Okay? K1 ends up at the root, K2 is here, and then we never change the actual depth of this side, and it breaks. Okay? So you can't do the one single rotation business with a left-right or right-left insertion. Okay? Well, what do you do then? Okay? Too deep, so what do you do? Well, sorry about the letters. It's a conversion from my Mac. You can do this thing we call a double rotation. Okay? You can think of it as 2 single rotations, but a lot of times that actually confuses the issue a little bit. Okay? If you do it. Instead of 3 subtrees, okay, see how this has like 3 total subtrees here, and then this is a subtree and this is a subtree? What we can do is we can break this one into like 2 subtrees of its own, where we are adding another kind of a node at the top. We're like just saying, look, let's expand this guy and see what's actually going on a little bit deeper under the covers. Okay? All right, so we did that. We just kind of said, fine, it's going to be still the same level, and everything's the same. We just said, let's break this up and see what's going on. Node here, and then subtrees here and here. We don't know which one of these was actually lower at this point. I mean, when we do it, we'll find out. But it doesn't actually matter. Okay? Watch what we do. Okay? Here's the double rotation. We can't leave K3 as root, because we know we've already got a problem. Okay, with K3. It's 1 here and 1, 2, 3 on this side. Not going to work. Nor we can't make K1 as root because we tried that already. That didn't work. So the next one we have to try is to make K2 here the root. Okay? So what do? Well, you do the same thing. You grab K2 and you kind of drag it up here, and then you have to figure out what's going on. Well, the nice thing is, okay, that K1 has to be what? It has to be less than K2, and K3 has to be greater than K2. So you've got your sides already, and then everybody else you just have to figure out as well. It's not actually that hard when you do that figuring out. If you're doing it recursively, it's actually relatively simple. But you now have K2 up here, and let's see, B has to be smaller than K2, so it's got to be on this side of the tree. My thing is definitely dying now. Okay, it's got to be over here. I'll use this one. The B here has to be on the left-hand side of K2, so it's got to be down here somewhere. And C has to be on the right, so it's got to be down here somewhere. And it's going to fit in somewhere in the other two subtrees. Okay? A little trickier because you have this kind of double rotation. Okay? Let's see how this one. You can also fix it I'm going to show you the exact same animation in a minute. You can also fix an insertion in the left subtree of the right child the same way. So see how this K1 is still broken here because you've got 1 and you've got 1, 2, whoops, sorry, 1, 2, 3 here. Not there. For the right child left subtree, you can actually, same thing here, you can fix this doing a rotation the other direction. Okay? Same thing in this case, K2 still ends up on top, and everybody filters down where they need to go. Okay? All right. All right, let's try this. Now we're going to do the same thing as before, except we are going to insert into, we're going to insert this, we're going to start with the tree we had before. Then we're going to do 16, 15, 14, 13, 12, 11, 10, 8, and then 9. Okay? Let's see how this works. Okay. This is where we might end up with our tree not fitting on the page. Okay. So we're going to insert 16. Let's see what happens. Okay. we insert 6. This is the same one we started with before, we ended with before. OK, 16 goes down here, goes all the way down, and it's there, but we're fine. No need to actually change anything here. OK, nobody's actually affected. Nobody, no harm, no foul. OK, let's put 15 in there. OK, 15 is going to come down to the left of 16, and I bet we have a problem. OK, there we go. Let's see. 15 goes in. It goes down, 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 and then left. And it is the right subtree. Let's see who's got the problem. We'll pause it when we get to the problem one, the first one here. OK? All right. Then, whoops, so I didn't pause it. Well, let me go to the back. All right. I'll do another one. You'll see what happened. But this one actually, as it turns out, it was only a single replacement, right? You saw that we didn't have to do a double rotation on that one. So it didn't actually matter. Okay? Let's do 14. Okay. 14 is going to be very similar. Okay, it's going to go down, down, and to the left now. And now we're going to be the left and the right subchild. Okay? It's going to go back up here, and then this one has got the problem now. Okay? Or does it? Actually, nope, it doesn't. Sorry. This one does, right? Because now you've got I wish my pointer was working. You've got a 3 on the node number 6, right? It's got, what, how many this side? 3 and then 1. So we've got an imbalance. And that's the one we're going to have to change. And now we're going to have to do this double node change here, or this double rotation, where we're going to say, OK, this one's got the problem, OK, and it was in this one here. So it's going to end up being this one that gets dragged up. Let's see, I think. Did I have that right? I think I did it backwards. But anyway, that was the double rotation in there. OK, let's see another one. That one was 14. Let's do 13, 13, et cetera. OK? And then let's see. That one's going to go there, and then down here and to the left. OK. Oh, we're going to run out of space here in a minute. I won't make you go through all of these. OK. And then this one is OK. This one now has a problem on its right and its left. OK. You do a whole double rotation. You want to see that one again? Yeah. Let's see. That one was, what did we just put in? 13? Yeah. OK. 13. I'll stop it and we'll talk about it. OK. All right. And then 13 goes there. Walks back up. OK. OK. And then there. Oh, pause. There we go. All right. So that's the one with the, there we go again with the thing. OK. So that's the one with the problem, right? This is the one with the problem. And why is it a problem? Because the right subtree is a height of 4, and the left subtree has a height of 2. OK. And how do we do a double rotation? OK. Well, you go down to where it actually got inserted. OK. And, well, let's just see. Oh, is this one only a single? You're right, it is. It's a right subtree of the right child. Yeah, that's right. This is only a single. Hang on. Yeah, why is it a single? Because it was a right subtree of the right child. 13 went of this one. 13 was in this side of this one. Thank you. OK, and there we go. OK. 7 was the one that got moved up because that was the top one there. All right, I will do one more. Let's see. Let's see. That was 13. Let's do 12. See if that changes it. There's a reason for doing all these, right? 12 goes, OK. 15, 14, 13. Oh, this might only be a single two. Let's see. And there. And then 0 and 2. So that's going to be a single rotation. Right? And then we didn't have to change again. OK. And then, sorry, that was 12. We're going to do 11. 11, like this. Let's see. All right. Right, left, left, left. All right. And then This one is going to be 2 there, and it's going to update to 3 here. So now we're going to have a problem on this one, and it was a left-left, so still only a single. All right, and then I'll get to another double here in a minute, I think. 10, did we just do 11? Yes. 10 goes down, 13, 12. OK, now I think we met. Let's see. No, actually, I don't think we'll have a problem, will we? It'll be 4 and 3. This is why we have these big, long examples. We'll have a problem there, but not at the top one. All right, and then that was 10, and then 8. Oops, not 87. Insert 8 and see what happens. OK, 8 is going to come down, and it's going to go right again, and then left and left and left, left and left and left. OK, and then it's going to climb up, and still good there. We are now good, and then this is where we've now got a problem, right? Or did it not have a problem? No, everybody was OK. Yeah, 4 and 3. We're still OK. All right, there's one more. I am going to make you do all this. OK, and then let's insert 9. OK, I'm going to actually do this and then move this over so we can see it. There we go. OK, so now 9 is going to go in here. OK, so 9 is going to come down, and 9 is going to go to the right here. I'm sorry, right here. OK, and now we climb up. All right, and then, no, it's only going to be right there. And then, yeah, that's it. So actually, we're OK. All right, no more doubles. I'll have to find a better example for doubles next time. Yes?
Can you skip like 5 steps before and then see the double rotation? I think it was.
Which one? Do you remember?
Yeah.
Whoops.
Like 6 steps before.
Let's see. All right, hold on. All right, let's see. We've got, which one do we have? We're doing 16, 15, 14, 13, 12. So let's see. 16, 15, looks like 14.
Now you want to insert 8.
Now you want me to insert 8?
Yeah.
I'm sorry? Works with 14? Yeah. Let's do 14. All right, let's just see what happens here. All right, so 14 comes in. All right, so I'm going to pause it when we get to the bottom here. All right, so 14 comes in, and it ends up on the right-hand side of this one here. OK, all right. Who's going to have the problem now? Let's see. 6 is going to have the problem because this one's going to get 1 bigger. This is going to now go. This one's going to go to 2. This is going to go to 3. So this is going to be 3 and 1. OK, and it was a right-left insertion. So we do need a double insertion, or a double rotation, rather. All right, so it's going to be fine there, fine there. OK, and then fine here. I'm sorry, not fine here. Here's where we've got the problem. OK, so how are we going to do this? We're going to go to the right subtree here. OK, it's not going to be this one. We're going to grab this one, and we're going to shake it. And then it's going to end up being higher than this one. OK? All right. There we go. Boom. OK? If you want to go check that out, the slides are online to show you the actual order of everything. Yes?
Is it possible to do 2 rotations down?
No, that's what's nice about it. You don't actually have to do 2 rotations. You just do 1 rotation, either a double or a single, and the rest takes care of itself. Think about it this way. If you are making this one balanced down here, well, up farther in the chain, it started out balanced before. We knew it had to be. We only moved it at most 1. And so now we're at least backing it up 1. So then the one above it must be OK as well. OK? Yeah. Good. OK. All right. Whew. Made it through that one. OK. So that's the AVL code. Whoa, this is small font. Sorry. Coding the rotation, OK? This is, like I said before, is I'm not going to make you guys do it. OK? I may make you, like on the midterm or something, draw some of the rotations. But I'm not going to make you actually code it right now anyway. But doing the recursive solution is the easiest. If you try to do a non-recursive solution, you can get tripped up really easily. OK? And in the case of the recursive solution, like we said, it's actually not a bad idea because you don't have to recurse too many times, so your stack is probably going to be okay. Okay, and what we basically do is we insert a node just like normal binary search tree, like we were doing, and then you check if the height of any subtree changes. Okay, if it doesn't, you keep going. Okay, if the height does change, you do the rotation, and then you update as you go. And it's a recursive call, so as you go, you will figure out if you need to do the rotation or not. And you can always do one rotation, and it'll suffice. I didn't write this code, but I found a really good AVL tree, very relatively short solution on this website here. So if you want to go, the website's listed in the slides. If you want to go there and check it out. Okay, written in C++. All right, questions on AVL trees? Whew. There's a lot of stuff right there. The dirty little secret, though, I forgot to say, nobody ever uses these. In practice, okay, you actually don't use I probably shouldn't have given you that secret. In practice, AVL trees are not used that much. There are other similar sort of rotation algorithms that aren't as easy to understand as this one, that are a little better in some other forms of this keeping your tree balanced. But I want to show you this one. It's a good one. It's just not in practice used as much as some of the other ones. So, shouldn't have told you that. Then you'll start using them, and then I don't want to say that anymore. OK. All right. Last thing I want to cover, kind of briefly, is it possible to represent a tree in an array? We've done trees so far as linked structures, with the links as being a node, and then a node as a right child and a left child. Can we somehow shoehorn this in to an actual array that has a fixed size and fixed indexes? I bet you can guess the answer to that. All right. But we have to talk about a couple different things here. We're actually going to talk about representing complete binary trees versus full binary trees. So take a look at this, another little bit of definition here. A full binary tree is where every node of the whole tree is filled. Okay? And it's binary in that there are no empty spaces. The only things that don't have any children are the leaves. Okay? So that's what the full binary search tree. We can have a complete binary search tree where we have gone down the route of doing a full binary search tree, but some of the leaves or some of the nodes are left untouched. Only the ones on you have to keep filling in left to right, basically. Okay? So each level is as deep as it can go. Each level is as deep as it can go, except that the last level may have some empty spots here because we haven't quite gotten to fill them yet. Make sense? We've got to fill it in this order: 6, 2, 8, 1, 5, 4, 3, 1, 5 down here like that. Okay? This is not a binary search tree, it's just a binary tree. Okay? That's what a complete binary tree is. All right. I'm seeing some people still writing this. The nice thing about having a binary tree is that you can do some arithmetic and you can actually work things out. Okay? I'm still watching people write. I just hope I hope some of you aren't like writing a letter, actually writing stuff down. Okay. All right. So no, don't worry. All this is online too, of course. Okay. All right. Here's what we need to do. We need to figure out a strategy to, like I said, shoehorn that tree over there into this array such that it makes sense. And we aren't going to be allowed to have pointers anymore. This is not a situation where throw a node in there and it's going to have its own pointers left and right. We are going to get rid of the actual left and right pointers on this thing. Okay? Anybody want to give me a strategy how they might, what might be a good thing to put at the beginning of your array? Yeah, the root, right? So we might want to do this. So if we do this, so this is, remember, this is an array. This is just an array. Remember, this is 0, 1, 2, 3, 4, 5, 6, 7, 8 in this case. Okay? It probably is not a bad idea to put a in the 0th part, because that's the root. So if you have an array of a tree, and you go to the first element in the array, that's going to be the root of your tree. Okay? What might we want to put in next? Elaine?
The left child?
The left child, why not? We could do either, right? But remember, we're going to be filling this thing left to right. So yeah, so then we maybe put B there, and then what could we do? We got a couple choices here. What can we do now? I mean, there's only a few choices, yeah? Put in C. OK, that's one choice. I'll put it like this. That could be one choice. What's another choice we could have done? D, right? OK, and then if we were going down the path where we did C, then maybe we'd put D here. And we could have put maybe H. And then, so we could put it in different orders. OK? But as it turns out, the ones who said C actually make a little bit of sense. If you do it level by level and kind of walk your way down the tree in this level order solution here, OK, then we can actually do it like that. Each level gets its own, or each level goes in one after the other, like that. OK, now we've got the tree, and it's in this form. And what's cool is now we know the index, and we don't know, and we know the actual symbol. We do not have any links. So there are no more like you're the left child of this, you're the right child of that. But this is the cool part. OK, we've cleverly put this in. We've done it in a nice orderly fashion, and order wins in this case. Because what we can do is now we can say, hey, here's a little bit of math, just a little arithmetic. We said that the root is always at location 0. If you are at a non-root node, the parent is always at I minus 1 divided by 2, and you got to use integer arithmetic for this. So, for instance, let's go to D here. Okay, we're going to try this one right here. D's parent is B. See if we can get there. D's index is 3. 3 minus 1 is 2. 2 divided by 2 is 1. So therefore, we say that D's parent must be at location 1, which indeed it is. Kind of cool? Same thing for all the other. You can do the same thing for the other ones. If you want to find a child, you can do a similar bit of arithmetic. Okay? The left child for some element is always at 2 times that element's index plus 1. And the right child is 2 times that element's index plus 2. All right? Let's look at D. D again. We'll look at D, and it says, so we want to find its children. Well, 3 times 2 plus 1 gives you its left child. 3 times 2 is 6 plus 1 is 7. That would be H. Check. Okay? This one right here. And then 3 times 2 plus 2 for the right child gives you 8. And that's where I is. Pretty cool. Okay? So we can shoehorn this in here. We don't always want to do it this way, but what's nice about this, we have minimized completely the amount of information we have to hold around. Like the structure of the array holds all our information. If you know a node's index, you can find its parents and its children by doing a little quick arithmetic expression. Pretty quick, pretty easy. Okay, makes it a lot faster if you've got things like this. And by the way, when we get to some other data structures, we'll see this method again, and you'll get a refresh on all the math we have to do for this stuff. Okay? All right. You don't have to keep the pointers. You only have to keep track of the array and how much of that array is actually used, because you don't want to walk off the end. Like, for instance, F does not have any children. If we wanted to find F's left child, we would say, let's see, F is 5. We would say 5 times 2 plus 1 gives you 11. Well, look, we don't even have 11 or 12 items in this. And so it's bigger than it. So you need to do a little comparison and see if you're over the edge there. Okay? The links only exist in the formulas themselves. There's no like other link pointer. You don't need it. Not necessary. Okay? Based on your position. Kind of cool. Okay? All right? This is what I was talking about earlier with this thing. Can we do print post order with this sort of solution? Sure. You don't have a recursive like calling the next node. Like you're not passing a pointer. You're just passing an index back and forth. So let's see what this one says. It says if index is greater than or equal to count, that's how many we have in the tree, then return. We cannot find that element. It does not exist in the tree. Otherwise, recursive call. Print post order index times 2 plus 1. Index times 2 plus 1 is the left child, right? Then you do print post order index times 2 plus 2 gives you the right child. Okay? And then you actually print the node. So it's exactly the same as what we talked about like last week in terms of going through in order. You can do that with an array. You don't have to have any links, no pointers necessary. You need one pointer for where the array starts. That's it. Okay? It's kind of cool. Kind of a cool idea. Questions on that? No? All right. Can we represent non-complete trees using this? Like, is there a way to represent, say, a binary search tree in an array? Do you want to do that? I mean, I guess that's a more philosophical question, I suppose. But if you want speed, all right? I mean, if you want speed, yeah, an array is not a bad way to do it, right? No following links and passing pointers around and whatever. Can you do this? Yeah, I don't see why not. Let's just represent unused indexes with some plug a value in there that you know isn't going to be a value in your tree. So let's say you're only doing positive values in your tree. Stick negative ones in there as your values to begin with. And then if you see a negative 1 when you try to go to some node, that means it does not have that child on that node. Okay? So let's see. Could we represent this tree this way? All right? Let's see if we can do it real quick. All right? I'm sorry, the font's kind of hard to read here too. But so 5. 5 is going to go where in this tree? 0, right? We're just going to put, whoops, sorry, that should be a 5. 5 is going to go there. OK. 6 is the right child of 5, right? The right child was 2i plus 2, right? So it's going to be 2i plus 2. So we're going to cross that one out. That's going to be 6. OK? And then 6's left right child is 2 times 6's index plus 2. So 2 times 2 is 4 plus 2 is 6. So now 9 is going to go here. And the left subchild of 9 is going to be 2 times 9's index, which is 6 plus 1, 13, right? So 7 is going to go in location 13 here. Whoops, 7. Got too many numbers here. OK. All right. What's the problem with this method for this kind of binary search tree? Anybody see what the problem is if I add another, like a right to the 7? Yeah. You got a lot of empty space. Yeah. This is what we call a sparse situation, where there's too much empty space for what you need to do. Now, if we were keeping a balanced tree, like an AVL tree or some other balanced tree, we would fill in a lot of these numbers in the meantime. Because as long as it's balanced, most of the numbers in between are there. If you want to, for every level down deeper you're going, how many more pieces of our array do we have to keep? How much is lots? Twice as much. Yeah, we have to keep twice as much. All right, because if you go one more level down, you've got to have at least 16 elements in there, and then 32, and then 64, and then all of a sudden, you're in deep trouble if you keep a non-balanced tree. So another good reason for keeping balanced trees. OK. Any questions on this stuff at this point? All right. Then I guess we'll see you guys either in lab or on Wednesday.